Based on the information provided, the recommended cable size is 500 mcm copper according to National Electrical Code, Section 310.16. This size ensures sufficient ampacity for future expansion and aligns with current NEC guidelines. Let's delve into grounding. Install a 3/4 inch diameter, 8 foot long copper-clad steel ground rod. Ensure the ground rod is driven into the ground until the top is at least 2 feet below grade. While not required by code, adding a second ground rod provides additional safety and redundancy. Install a second 3/4 inch diameter, 8 foot long copper-clad steel ground rod approximately 6 feet away from the primary ground rod. Connect both ground rods together with a 6 American wire gauge solid copper grounding conductor. Use 1/0 American wire gauge copper wire for the grounding conductor. Connect the grounding conductor to the ground rods using copper ground rod clamps. Run the grounding conductor to the service entrance equipment and connect it to the ground bus. The entrance cable should be sized appropriately for the anticipated load. Install a 3-inch weatherhead to protect the entrance cable from moisture and weather conditions. It is recommended to obtain a proper load design for future expansion to ensure the electrical system can safely handle the anticipated load. Now let's discuss the details of cable sizing. National Electrical Code, Section 310.16 provides ampacity ratings for various conductors based on their size and insulation type. For copper conductors, the ampacity increases with the conductor size. Selecting the correct conductor size is crucial for safety and performance. An undersized conductor can overheat, leading to insulation damage and potentially causing a fire. An oversized conductor, while not a safety hazard, can be more expensive. The 500 mcm copper conductor is chosen to accommodate the existing load and provide ample capacity for future expansion. This helps to avoid the need for costly upgrades later on. Moving on to grounding, the primary function of a grounding system is to provide a low impedance path for fault current to return to the source. This helps to ensure that protective devices, such as circuit breakers, operate quickly to clear the fault and prevents electrical shock hazards. A properly installed grounding system also helps to minimize voltage fluctuations and improve the stability of the electrical system. The 3/4 inch diameter, 8 foot long copper-clad steel ground rod is a common type of grounding electrode. The copper cladding provides good corrosion resistance, while the steel core provides strength and rigidity. Driving the ground rod to a depth of at least 8 feet ensures that it makes good contact with the earth. Burying the top of the ground rod at least 2 feet below grade helps to protect it from damage and corrosion. Adding a second ground rod, while not always required, can significantly improve the effectiveness of the grounding system. The 2 ground rods provide parallel paths for fault current, reducing the overall impedance of the grounding system. This can help to improve the speed and reliability of protective device operation. The NEC recommends that if multiple ground rods are used, they should be spaced at least 6 feet apart. This helps to minimize the interaction between the ground rods and ensure that they provide independent grounding paths. Connecting the ground rods together with a 6 American wire gauge solid copper grounding conductor creates a bonding path between the 2 electrodes. This helps to equalize the potential between the ground rods and further reduce the overall impedance of the grounding system. Using 1/0 American wire gauge copper wire for the grounding conductor ensures that it has sufficient ampacity to carry the maximum fault current that may occur. The grounding conductor should be installed in a direct and unobstructed path from the service entrance equipment to the ground rods. Copper ground rod clamps are used to make a secure and corrosion-resistant connection between the grounding conductor and the ground rods. These clamps are typically made of bronze or copper and are designed to provide a low-resistance connection. The grounding conductor is run to the service entrance equipment and connected to the ground bus. The ground bus is a conductive bar that serves as the central connection point for all of the grounding conductors in the electrical system. The entrance cable, also known as the service entrance cable, is the cable that brings power from the utility company to the building. The entrance cable should be sized appropriately for the anticipated load, including both the existing load and any planned future expansion. An undersized entrance cable can cause voltage drop and overheating, while an oversized cable can be more expensive. A 3-inch weatherhead is installed at the top of the service mast to protect the entrance cable from moisture and weather conditions. The weatherhead should be installed in accordance with the manufacturer's instructions and local electrical codes. Obtaining a proper load design is essential for ensuring that the electrical system can safely and reliably handle the anticipated load. A load design should take into account all of the electrical loads in the building, including lighting, appliances, equipment, and any planned future additions. The load design should also consider factors such as voltage drop, conductor ampacity, and overcurrent protection. In summary, firstly, select the appropriate cable size, which in this case is 500 cm copper, based on NEC section 310.16 to ensure sufficient ampacity for both current and future needs. Secondly, install a primary ground rod that is 3/4 inch in diameter and 8 feet long, driving it into the ground until the top is at least 2 feet below grade for effective grounding. Thirdly, consider adding a secondary ground rod, positioned approximately 6 feet away from the primary rod, and connect them with a 6 American wire gauge solid copper grounding conductor for enhanced safety and redundancy. Fourthly, use 1/0 American wire gauge copper wire as the grounding conductor, securing connections with copper ground rod clamps, and ensure it runs to the service entrance equipment connecting to the ground bus. Fifthly, size the entrance cable appropriately, taking into account the anticipated electrical load to prevent voltage drop and overheating. Sixthly, install a 3-inch weatherhead to safeguard the entrance cable from weather elements, ensuring it complies with manufacturer instructions and local electrical codes. Seventhly, conduct a thorough load design that considers all present and future electrical loads to guarantee the electrical system's capability to handle the anticipated demand safely and reliably. By following these steps, you can ensure a safe and efficient electrical system that is prepared for future growth. Remember that proper electrical work requires knowledge and adherence to local codes and regulations. Consult with a qualified electrician if you are unsure about any aspect of the installation. Always prioritize safety when working with electricity.